Alright, so in this chapter 13, we're going to be focusing more on solutions that we've been talking about, specifically these aqueous solutions. First section, I'm talking about whether a precipitate will form and just the difference between strong electrolytes and weak electrolytes. Looking at, first of all, we're going to define what's called dissociation, which is really just the dissolving of ions into their components. You've got salt, for instance, separating into its positive sodium ion and its negative chlorine ion is really how it exists in a solution. Same with calcium chloride. Just note that when calcium chloride breaks down, because there are two chloride ions attached to every calcium, you're going to see twice as many moles of the chloride ion, the negative chloride ion, compared to the positive calcium ion. So here's just a picture of what you're seeing. Those partially charged, you have the water with a partial charge on each side, kind of incentivizing the sodium and the chlorine to split up into its atoms, into its ions, the negative side being attractive to the positive sodium ion and the positive side of the water being attached to the negative chloride ion, and it works its way through doing just that, and you'll see the salt break down and obviously still be in the water, but it's in the form of ions. So we just want to look at a sample problem talking about how many ions we'll see, how many moles of aluminum and sulfate ions we're going to see in this dissociation process, looking specifically at aluminum sulfate. So I have, starts with Al2SO43. Pen's not working there. Let's use different color. So Al2, just a sec. So that's going to break down. You're going to have 2 moles of aluminum with the positive 3 charge is what aluminum will make. And then if we look at our ion sheet, we're going to have 3 SO4s. And if you do have your ion sheet handy, you can see that SO4 would have a negative 2 charge. So if I have 1 mole of aluminum sulfate, that means I'm going to have 2 moles of aluminum ions and 3 moles of sulfate ions. So specifically talking about the type of reaction that forms a precipitate between 2 solutions, you're mixing 2 essentially liquid substances together, and a solid will form, giving evidence for a reaction. There are no ionic compounds that are completely insoluble, but we will see very low solubility and consider that insoluble. So if it really is hard to dissolve, doesn't dissolve well at all, we will consider it, for our intents and purposes, insoluble. So here are the rules, and it's good to have these handy. I'll put a copy on Canvas for you, but and different books will use different sort of sets or varieties of these rules in different ways. But we do want to look at, we have here anything with sodium, potassium, and ammonium we're going to consider soluble. Anything that ends in nitrate, acetate, and chlorate we'll consider soluble. When it comes to chlorides, most of them are going to be soluble, but if they start with silver, mercury 1, or lead, they will be considered insoluble, though lead 2 chloride will be soluble if you heat up the temperature. Most sulfates are soluble. The ones that start with barium, calcium, mercury, strontium, and lead are not, though. And then if we have carbonates, phosphates, or silicates, we're going to consider those insoluble unless they have sodium, potassium, or ammonium. So you have to be aware of those exceptions. And then sulfides tend to be insoluble, and except those of calcium, strontium, sodium, potassium, and ammonium. And I just want to make it clear here when we say soluble, like these ones, we're saying that they are considered aqueous in solution. They're dissolved in water. Things that are insoluble, we're going to put a parenthesis after the compound and say that it is solid because it didn't dissolve. So here's some examples so you can see. We can use our chart to figure these out, but we have nickel chloride. We've got potassium permanganate. We've got copper 2 sulfate. We've got lead nitrate, and we've got silver chloride and cadmium sulfate. So let's use our rules to verify what we're seeing in the picture. First one is nickel chloride. I see that most chlorides are soluble, and I don't see nickel in an exception, so we are going to say, sorry, I almost wrote S for soluble, but I want to say aqueous there. So that one's going to be aqueous. We look at our potassium compound. Again, potassium tends to be soluble, so we see it aqueous. We don't see any solid in there. Copper sulfate. We see sulfates. Most are soluble, and copper is not one of those exceptions. So again, we're going to say aqueous. Lead nitrate. We look at nitrates. Rule 2 there. Nitrates are indeed soluble, so it should be aqueous. Now we're starting to see some precipitates forming in the last two. So we look at silver chloride. Chlorides are mostly soluble. Notice, though, there's an exception for silver, so that's why we see the precipitate. And cadmium sulfide. Let's see, do I see sulfides number 6 here? Sulfides tend to be insoluble, and I don't see cadmium as as an exception. So again, that will form a solid as well. So you can see how we can use that list to make those predictions, whether or not those compounds will be soluble or remain a solid in water. So the next big thing we want to talk about in this section is net ionic equations. And a net ionic equation really breaks down what we see in terms of the ions that are actually dissolved in the solution. So we want to make a definition here. We've got the spectator ions. Those are ions that actually don't really do anything. They stay ions before the reaction, then they stay ions after the reaction. So they're called spectators because they're really just watching the action, not partaking in it. An example here, we've got cadmium and a nitrate and an ammonium and a sulfide, all dissolved in ions in the water. However, because cadmium sulfide is insoluble, it's going to form a precipitate and leave the nitrate and the ammonium as ions in the water. So what happens is we see the ones that are crossed out, they appear on both sides. We have nitrates on both sides. We have ammonium It's on both sides. So we're just going to limit it down to what's actually happening in that reaction. And you have cadmium ions meeting sulfide ions to form cadmium sulfide. And notice that those two were aqueous before the reaction, and they became solid as a precipitate during the reaction. Here's another example of a net ionic equation if you'd like to see it. We've got potassium sulfate combined with barium nitrate, both in aqueous solution. However, when we mix them together, we see they go through a double displacement reaction. So now the potassium is paired with the nitrate. The barium is paired with the sulfate. So if you notice, the outside ions are paired with each other, the K and the NO3, and then the inside ions are paired with each other, which would be the Ba and the SO4. Remember, the positive ion always gets listed first when we look at it over on the other side. So now notice, if both of these were aqueous, we wouldn't really have a reaction, but because barium sulfate does become solid, we see that as evidence that a reaction took place. So when I break this down, and I'm going to zoom in, this is probably a little small. When we look at the total ionic equation, I'm going to break everything down into its individual ions to write that out. So potassium, the K, was a K plus. You might need to use your ion sheet if you forget what these ion charges would be. But K plus, and there's two of them, so we're going to write that. We're going to notice we take this subscript and we put it in front as a coefficient. So we're going to have 2K plus SO4 minus 2. There was only one of them. And then we have barium plus 2. All those are aqueous so far. And we're going to separate the NO3 out, again changing that subscript to coefficient. So we have 2 NO3 with a minus 1 charge. Everything's aqueous before when they dissolve. And then we see the reaction happening, a precipitate forms. What we would do is we would look at our solubility rules a couple slides ago. We would see if potassium nitrate is soluble or insoluble. And because it's soluble, both of those are aqueous. However, if we look at barium sulfate did not dissolve. It's not soluble. It's insoluble. So we're going to see barium sulfate as a solid. It's our precipitate in the reaction. So the net ionic equation, I can cross out my my ions that appear as aqueous on both sides. So I can cross out the potassiums, I can cross out the nitrates, and I'm left with the sulfate and barium ions that were aqueous before have now become solid. That's the net ionic equation, the actual total reaction that's taking place. I shouldn't say total, but the essential part of the reaction that's taking place. So we're going to look at an example here. Identify the precipitate that forms when aqueous solutions of zinc nitrate and ammonium sulfate are combined. Write the equation and the possible double replacement reaction. Then write the formula equation, the overall ionic equation, and the net ionic equation for the reaction. So a lot going on here, but we can do it all. I like these problems because they really show a lot of the chemistry we've learned over the past couple of years. So we're going to look at zinc nitrate. Now, first we have to figure out the charge of each. So let me get my ion table. I'm going to be using this a lot this chapter if you don't have your ions memorized. So zinc is going to be a +2. So zinc has a +2 charge. Nitrate is NO3 with a -1 charge. Ammonium is NH4 with a plus charge. And sulfide is S with a -2 charge. So So remember, when zinc and nitrate combine, you're going to have 2 nitrates for every 1 zinc. So it's going to look like zinc, ZnNO3, 2. And because they're in aqueous solution, we're going to put AQ. And then we've got ammonium sulfide. It's a 2 to 1 again. So we have NH4, 2, S in aqueous solution. Now when I see if the double displacement reaction happens, again, I take the outside ions, so the zinc and the sulfur, and combine those. They cancel each other out because they both have a 2 charge. So it's just going to be ZnS. Then we've got the ammonium and the nitrate coming together with the same charge. So it's going to be NH4NO3. And we need to figure out if those are aqueous or solid. So I look at my rules for sulfides. Sulfides are insoluble, and zinc is not an exception. So that tells me right away that I have a solid formed. So zinc is a solid. And NH4NO3, we go back to our nitrates. Nitrates are soluble. So nitrates will have an aqueous after it. So the reaction did happen. Let's balance it real quick. We have 2 nitrates on this side, 2 ammoniums on this side. So I see the easy fix is just to put a 2 in front of that. And what we're going to do here is break each of these down into their ions. So zinc will have a +2 charge. There's 2 nitrates, so I'm going to put the 2 as a coefficient with the minus charge. Again, make sure these are all labeled as aqueous. And then NH4, you're going to have 2 NH4s with a positive charge. Make it aqueous. And then you're going to have a sulfur with a -2 charge. Again, aqueous. Notice the zinc sulfide became solid. So I'm going to leave that alone in its solid form. And then we have 2 NH4s that are aqueous. And don't forget to bring this 2 with the NO3 as well. And it is aqueous. So notice I broke everything down into its individual ions. Made them all aqueous except for the precipitate. Now I get to cross out all my spectator ions. So spectator ion, meaning it stayed aqueous on both sides. So the nitrate stayed aqueous on both sides. The ammonium stayed aqueous on both sides. Zinc and sulfide did not. They are what combined to form the precipitate. So you could technically go without that middle step. Not sure what's going on there. Sorry about that. You could technically go without that middle step, making your total ionic equation. But this is your total ionic equation. This is your net ionic equation. Because what's actually happening is just the zinc and the sulfide combine to make zinc sulfide. So that's from start to finish. That's a lot, so we're going to have to take some time to practice this. But from start to finish, how you are taking your, making an equation, putting the ions together, figuring out the double displacement, how that would work, figuring out what's solid, what's aqueous, balancing it, breaking it all up into its ions, crossing out the spectators, and then finally coming up with your net ionic equation. Trust me, I know that is a lot. We're going to do some extra practice on this, work together, try to figure this stuff out, and then hopefully we'll all be pros by the end. If you have any questions, let me know.